In these notes for 8.2, we're going to look at function compositions, which essentially are what you get when you use one function as the input for another function. So we're going to plug an entire function into another one. And the notation for that, you can write it two ways. One, you can use this little circle, or you can completely put one function into the input parentheses of another one. So both of these you would say f of g of x, or the composition of g onto f, but f of g of x is fine. We're going to plug the g function into the f function here. So for example one, what we'll do is for each pair of functions, we're going to find first f of g of x, and then we'll find g of f of x. So we're going to put them into each other. Okay, so first, for this first one, we have f of x is 2x minus 5, and g of x equals 4x. So first, let's find f of g of x. So what we're going to do is put g, the 4x, into the f of x function where x is. So instead of 2x minus 5, it'll be 2, and then where x is, we'll put 4x. And then we just simplify it. 2 times 4x is 8x, so this is 8x minus 5. And now let's do the opposite. Let's find g of f. Okay, so we're going to put 2x minus 5, which is the f of x function, into the g of x function for x. So instead of 4x, we have 4 and then 2x minus 5, where x was, which gives us 8x minus 20. Slightly different results depending on which composition we are performing. For the next example, f of x is 2x and g of x is 2x plus 1. Okay, so let's first find f of g of x, which I could write like I did before, f and then the little circle and g, or I could write it f of g of x like this. It means the same thing. Those are two ways to write the same composition, right? Which is why I wrote that in up here. They mean the same thing. So anyway, and this one I think makes a little more visual sense for what's happening. You can see we're putting the g of x function inside the f of x function. But this way is a little faster to write. Okay, so instead of 2x squared, we're going to put 2x plus 1 and square that in for x. Okay, so we have 2x plus 1s being multiplied together. Right, that's 2x plus 1 squared. And remember, we have to distribute all of this together. So here we end up with 2 times 4x squared plus 2x plus another 2x plus 1. So we're going to multiply all that by 2 and combine like terms. So we end up with 8x squared. This would be 4x times 2 is 8x plus 2. And then let's finally find g of f of x. We're going to put the f of x function into the g of x function. Okay, so 2x plus 1, but instead of x, we're going to put 2x squared. A little faster on this one. We just get 4x squared plus 1. All right, now what we can do is also put an input on that. So we can find the function composition, and then we can put a number into it. Okay, so we're going to find f of g of 5 and g of f of 5. Now there's two different ways to think about this. We could find the function composition first, or if you write it like this, f of g of 5, you can see that one method would be to find g of 5 and then put that number into the f of x function. And that is potentially a simpler way to do that. I'll show you both ways here. So first, let's just find f of g of x. Okay, so I'm going to put the g function into the f function. So it's 2x minus 1 squared, which would equal 2x minus 1 times itself. So we're going to get 4x squared minus 2x plus 1, which is 4x squared minus 4x plus 1. And then I want to put 5 into that. So 5 squared here, another 5 here, plus 1 equals 25 times 4 is 100, minus 20 plus 1. We end up with 81. Kind of a lot of work, which I'm now going to erase. Apologies if you wrote all that down. Let's look at a slightly simpler way to do this. So let's find f of g of 5 from the get-go. So first, let's find g of 5. So g of 5, I'm going to put 5 into the g function right here. That would give me 10 minus 1, which is 9. So then f of g of 5, I'm going to put 9 into the f of x function. 9 squared is 81. Much faster. If you are given a number as the input, start with that. It's much quicker than figuring out the entire function composition. Now, finding f of g of x is useful if we were going to continually put different inputs into it. But if we're just finding f of g of 5, it is faster to first find g of 5 and then put that answer into the f of x function. Let's go the other way now. Let's find f of 5. And that's 5 squared, which is 25. And then we'll do g of f of 5. So I'm going to put 25 into the g function. That's 2 times 25 minus 1. So 50 minus 1 is 49. Much faster to just work with these numbers rather than try to find the overall function composition in terms of x and then plug the numbers into it. It still works, as you saw before, with the 81. It just takes a lot longer. So let's do that with the next one. I'm going to find f of g of 5 and g of f of 5. So first, let's find g of 5 over here. Going to put 5 right here. So that's 15 minus 4, which is 11. And then if I want to find f of g of 5, we'll use this notation this time. I'm going to put that 11 into the f of x function. So 11 times 5 is 55. And 55 plus 2 is 57. So g of 5 was 11. I can just plug that into the f of x function and get my 57. Let's go the opposite way. Let's find f of 5. So I put 5 into the f of x function. That would give me 25 plus 2, which is 27. And then if I want to find g of f of 5, I simply put that 27 into my g of x function. So 3 times 27 minus 4. That gives me 81 minus 4, which is 77. Okay, so the difference there between finding the overall function composition in terms of x and evaluating that function composition at a number, it's essentially the same work, but when you're evaluating at a number, it is often much faster and easier to find the values of those functions at the numbers instead of trying to find the overall composition. Okay, let's put this into a more real-world context. It says we make a purchase at a local hardware store, but what we've bought is too big to take home in your car. So you pay a small delivery fee. You pay for the purchase plus the sales tax plus the fee. The taxes are 7.5%. The fee is $20. So we're going to write a function t of x for the total after taxes on the purchase amount. We're also going to write a function f of x for the total including the delivery fee on the purchase amount x. Okay, so t of x, this is the total of our purchase plus taxes. So if the taxes are 7.5%, I'm going to pay 107.5% of my total. So my function t of x is 107%. That would be 1.075 x. So that's 107.5% of my purchase amount. So if my purchase amount is $100, I would pay $107.50. So just convert that 107.5% to a decimal, 1.075. Now my function for the fee, f of x, would be my purchase amount plus the $20 fee, x plus 20. So now I want to calculate f of t of x and t of f of x and see which is a lower cost. So first let's find f of t of x. Okay, so I'm going to put the t function into the f of x function. So I put 1.075 x in for x and then plus 20. So that is my f of t of x function composition. Now let's find my t of f of x. So I put the f of x function into the t of x function. So 1.075 times x plus 20. So you see now this sales tax is being applied not only to the purchase amount, but to the delivery fee as well. So I get 1.075x plus, and I'll need a calculator here, 1.075 times 20 gives me 21.5 or 2150. And there's that one. So now it says, which is a lower cost? Well, clearly, the only difference in these two functions is this number here. I have 1.075x plus 20 or plus 21.5. So the lower cost would be f of t of x. And that's because the delivery fee was added on at the end after taxes instead of before taxes. Now this says if taxes cannot be applied to delivery fees, which function composition represents your situation? And that would be the lower price one, f of t of x, because that had the delivery fee happening after the taxes. So that would be the 1.075x plus 20. So just a little real-world example of how function compositions can represent, an actual scenario from our lives. But essentially, function composition, you're placing one function into the other function as an input.